Still on the Scholastic Aptitude test preparatory questions. So based on the curriculum, we want to look at the topic, magnetism. So let's look at the following practice questions based on magnetism. Here is a part 4 of the tutorial. Question 1. A wire carries a current out of the page. Which diagram correctly describes the magnetic field of the wire? The keywords there are wire, current out of the page, magnetic field. So here we apply the knowledge of right-hand rule, the curled fingers versions. So the magnetic field forms circles around current carrying wires, which means option C and D are possible. But the right-hand rule indicates that the current is counterclockwise, which means option D is the only correct option here. Question 2. A wire carries a current I at a distance of R. The magnitude of the magnetic field is B. If both the current in the wire and the distance from the wire are doubled, the magnitude of the magnetic field changed by a factor of, that is, by how many factors does the magnitude of the magnetic field change? So the keywords here are wire, currents, distance, magnitude of the magnetic field. Now applying the formula, magnetic field B equals to mu naught over 2 pi multiplied by I over R, where B is the magnetic field, I is the current, and R is the radius. So we see that the magnetic field is directly proportional to the current and inversely proportional to the distance. So doubling the current and the distance, now we have the magnetic field to be equals to mu naught divided by 2 pi multiplied by 2I over 2R, which means doubling both the current and distance results in the same strength in the magnetic field, that is a factor of 1. So option C is the correct answer. Question number 3. Which of the following fields cannot change the speed of the object that is acted upon by each field? Uniform magnetic fields, uniform electric fields, uniform magnetic fields. So which of these fields is the correct answer? So the keywords here are fields, cannot change the speed. So we know that gravitational and electric fields can speed up objects and at the same time can slow them down when such objects move parallel to the fields. Nevertheless, however, uniform magnetic fields causes objects to circle at constant speed. So option C is the correct answer here. Questions 4 to 6. Negative charge Q moving with speed v in the positive x direction enters a uniform positive z magnetic field B, as shown in the diagram below. Question 4. What is the direction of the force of magnetism acting on the charge as the instant it first enters the magnetic field? So the keywords here are negative charge, enters a uniform positive Z magnetic field, direction of force. So this charge is negative. We apply the left hand rule. So if you point the thumb of the left hand in the direction of the velocity vector, so while keeping the finger straight, you point them out of the page. Then the palm is now oriented such that it pushes up the page in the positive Y direction. So option B is the correct answer. Question number 5. How is the magnitude of the force of magnetism acting on the charge affected by doubling the magnetic field? The keywords here are force of magnetism, doubling the magnetic field. So applying the equation F equals to QVB, where F is the force due to the gravitational force due to the magnetic field, F subscript B, force due to the magnetic field. So the force is equal to Q, which is the charge, V, the velocity, and B, which is the magnetic field. So the force of magnetism is directly proportional to the strength of the magnetic field according to the equation. So if I double the force and if I double the force, it means that the magnetic field is doubled. So I have 2FB equals to QV multiplied by 2B. So the magnitude of the force is doubled, meaning that option D is the correct answer. Question number 6. How is the acceleration of the charge affected by doubling its initial velocity? The keywords here are acceleration, doubling its initial velocity. Now, applying the formula Fc equals to Fb. Now, the force there, the force due to the magnetic field and the force due to centripetal acceleration. Fc is the force due to centripetal acceleration. Fb is the force due to the magnetic field. Don't forget F equals to ma, Newton's second law of motion. So F subscript C could be written as ma subscript C equals to qvb, because B is a magnetic field. So the question becomes MAC equals to QVB. So which means if I double the acceleration, I have 2AC, which will be equals to 2Q multiplied by 2V multiplied by B, everything divided by M. So doubling the velocity doubles the acceleration. So option D is the correct answer. Question 7. In the diagram above, a loop of conducting wires is placed into a uniform external magnetic field. A current runs clockwise through the loop, and the magnetic field is in the negative Z direction. The force on the loop is... So let's see which of these options is correct. Now the keywords here are diagram, current runs clockwise through the loop, magnetic field, force. So if we apply the right-hand rule, the straight finger version, we have, now the right hand is used for currents which are considered positive. When force is involved, the fingers are kept straight and point into the page in the negative Z direction. Now the thumb points in the direction of the current, that's the right hand thumb, points in the direction of the current, which is circling. Nevertheless, however, when the hand is placed at any point on the loop, then the palm of the right hand will always point outward and away from the center of the loop. So option B is the correct answer. Question number 8. Two parallel wires carry current in the same direction. As shown in the diagram above, one wire carries a 2 ampere current and the other carries a 1 ampere current. The force of magnetism acting on the 1 ampere wire is... So the keywords here are parallel wires, current in the same direction, 2 ampere current, 1 ampere current, force. Now, if you are to apply the right-hand rule, we observe that two parallel wires with current in the same direction will definitely attract one another. But the key to this problem is actually Newton's third law of motion. Action and reaction are equal but opposite. So when two objects interact, there is automatically an equal but opposite force between them. The only answer involving equal force in this question is option E. So the two different currents act as distractors. So option E is the correct answer here. Question 9. Questions 9 to 10. A rectangular loop of wire is moving toward and enters a uniform magnetic field at a constant velocity, as shown in the diagram below. The loop is shown in two positions: the initial conditions in solid lines and the final conditions in dashed lines or dotted lines, if you like. Question 9. Which statement is not correct for the motion shown in the diagram. So the keywords here are loop, entering a uniform magnetic field. Now you need to understand that magnetic flux is the intersection of the magnetic field and the area of the loop. Now initially, this magnetic flux was zero, but at the end, it reaches a maximum value. So option A is the correct answer. Now the last question, question 10. During the interval where a current is induced, its magnitude is, so what happens to the magnitude? The keywords here are loop, entering a uniform magnetic field, current is induced. Now we have the EMF, induced EMF, to be equals to IR, where I is the E is the EMF, I is the current, R is the resistance. Now, relating it to magnetic field, we can say E equals to BLV, where B is the magnetic field and V is the velocity. So, rearranging Ohm's law adapted for EMF to solve this current, we have E equals to IR becomes I equals to E over R. So, if you substitute for BLV from the motional EMF formula, we'll have I to be equals to E over R. And don't forget, E is BLV. So, we have I equals to BLV over R. So, option B is the correct answer. Thank you. God bless you.